Hello! Continue our last lecture. We were discussing application of Schrödinger equation. Today we're going to do a very interesting problem that is the beginning of understanding of many biomedical or biological in general phenomena. We're going to see what's happened with free electrons traveling when they find a finite barrier. What is a finite barrier? Well, a finite barrier is like a potential. So we have a potential, V of x, as I told you. The potential is always what represents the physical system. And this is a barrier here. So we have a potential barrier with some width, that's 2a. So the width of this barrier is 2a. And electron may come from minus infinite. So we have a flux of electron here. So here will be like a free waves propagating. And what is the energy of those electrons? You know, of course, we can put the energy above the barrier. Then it's not so exciting. But I'm going to say that the energy of this electron is below the top of the barrier. The top of the barrier has a value V0 in this region. So that is one region, and I put an electron with energy lower than the barrier. So that's the energy that the electron is coming. And then he finds this barrier. And many things can happen here. Well, classically, the electron cannot penetrate in a potential that's bigger than the energy. So therefore, classically, the electron will come back. But quantically, it's not the case. It's not true. The wave can penetrate in this barrier and survive after the barrier, in the space that comes after the barrier. And that's called tunneling when that happens. And we're going to solve this. This is in the Schrödinger equation, and we are able to solve. So the potential that we're going to consider is zero everywhere in space, except in this region that constitutes what we call a physical barrier. This barrier can be anything, can be a layer of water, can be a membrane, can be molecules that repels the electrons, can be anything, right? Can be empty space, nothing. If I have nothing there, that can be. So, it's something that the electron is not allowed. This is the classically forbidden region for the electron. We're going to consider electrons, particle, it doesn't matter. We are calling electrons because normally the electrons is a very important movable particle in everywhere. But these particles will come from the minus infinite. We don't know where they are formed and they are coming here. So there is a flux of particles coming. We normally refer to a flux of probability, an incoming flux of probability. And classically, as I told you, it will bounce back from the barrier. It will come to the barrier and bounce back. So classically speaking, there is 100% certainty that the particles will return. No particles will be found otherwise. If they have a single energy, of course. If they have a distribution of energy, some of them will pass through. Okay, so we're going to solve this problem using the Schrödinger equation. And as I told you before, in some example we solve, we're going to divide the space in regions to be able to connect them using the Schrödinger equation. So we're going to consider the first region, which is the incident flux, and probably some reflection. Then we're going to consider the one that's called classically forbidden, and then we're going to call the third one that maybe we have a flux of particle passing through, which is the transmitted flux. It's the region that if a particle exists here, they found a way to come back, to come to this region overcoming this barrier, and is not by passing on the top. Is a new process that only happens in quantum mechanics. That's the co-tunneling process. Okay, so if you understood right what I'm saying, let's start solving the problem. And by the way, I'm going to explain the solution here, because in many applications we're going to use a lot of flux of electrons coming in, going out, and then you have to know by head, you have to know right there what's the solution of this. So in the region 1, which is the part that particles are either coming or reflecting, so we are in the region 1 where particles are either coming or reflecting. We have the Schrödinger equation. There are free particles there, the potential is 0. Notice acting on the particle in that region. And we know the energy is the momentum squared divided by 2m. I can rearrange this, putting the energy as p squared divided by 2m. 2m cancel. P divided by h bar squared is the term in front of this psi. So the second derivative of psi in this region plus p divided by h bar square psi equal to 0. Again, I'm going to call p over k, which is the momentum. This is the wave number that normally we call momentum, because, it's the momentum. K and p is the same stuff. Therefore, what I can have here, if you remember, the derivative of the wave function give you the momentum. So I gotta get the derivative with one sign for the part coming this way, which is positive momentum, and one coming that way for negative momentum. Very well. The solution of this problem is plane waves. I could make combination of sines and cosines as I did before. But there is a very nice way of doing this mathematically, which is using the complex exponential. The complex exponential is already the combination of sines and cosines. And it's very interesting, because if I take the exponential and I take the derivative, I just get the momentum like expected from what I told you in many lectures before, which is the momentum of the particle. So it's very convenient to write, when I have a flux of particle coming to the positive x, by e to the ikx, because that's the solution of the problem. And when they have a momentum return minus ikx, because if I calculate the momentum, they will be in the opposite. So this part is the incoming part. Is the incoming part of the flux of particles. And the other one with minus ikx is the reflected part. So the solution is still combination of sines and cosines, the plane wave, and a better way to represent this is putting, because I can guarantee to you that exponential of ikx is solution of this. Just come and take, this is chi square. If you take one derivative, you get ik. If you get another derivative, you get another ik that gives minus. So you get minus k squared plus k squared times the function, and that's 0. This is very nice way to represent free particles, and you gotta know by heart that always you have free particles. You can put this, and depending on the momentum direction, you can either have ikx or minus ikx on the exponent. Okay, so the solution of the problem is therefore a combination of I to the kx, e to the ikx, or e to the minus ikx. That are the two possible solutions. Of course, we know that if you have a differential equation and the sum of the solutions is a solution. Now, I let here two amplitudes for those functions because we don't know exactly who they are, but we can determine them. Because I can ask to you, what is the probability of finding, oh, by the way, you can already understand that the amplitude of the wave is related to the probability, right? We already showed before. Therefore, if I tell you, I guarantee to you that I have a flux of particles coming this way. A flux of probability, right? It may be one particle, it may be trillions, that doesn't matter. We treat that individually. So, I guarantee to you that there is an incoming flux of probability. Then I ask you, what's the probability of a particle becoming from the minus infinite to reach the barrier? You're going to say, it's 100%. Because you guarantee to me that you made them somewhere and you shoot them to the barrier. So A must be 1. A squared, right, must be 1. So we have A as 1 because we want to guarantee that the particle is coming. They are reaching the barrier. Now, and then I say, well, B must be particles with the momentum opposite, as I just explained to you. And if I explain to you that those are particles reflected from the barrier, that's the reflection probability. And normally the reflection probability, we're going to call the square by R square, or B will be called R. So A will be 1, and B will be R. That's the way we represent the wave function on the part 1, because it's composed of part of particles coming, and that's 100% they will come. And then part of the particles that are returned. Now, I cannot guarantee they will return. They may stick to the wall, I don't know. Therefore, I have to keep the R as a possibility for the particle to return, to be reflected, right? It's a reflection on the barrier. So that's the wave function we must consider. And that's the wave function we always going to consider for that case. We have an incoming part and we have a reflected part. The reflected part, of course, has a momentum opposite to my axis, is returning. And the incidence is positive, is 1, is certainly with positive momentum. And this is here in this exponent. Okay, so that's the region 1. So we build up a solution that considers an incoming flux of probability, which represents particle coming, a reflected flux of probability, which depends on many conditions, as we're going to find out. But we left there the possibility. We don't know who is R yet, right? We know that the incidence must be 1, the amplitude, because we require 100% probability for what's coming. If we're not sure the particle is coming, we do not know what's going to be after it interacts with the barrier. Okay, now we go to region 3. In the region 3, which means after passing the barrier, I told you this is the transmission region. And if it is the transmission region, we must, on the part 3, we have a particle going to the positive direction. So the momentum is still going that way. So the exponent has a positive ikx. But we don't know with what chances the particle will pass to that part. So we left that in an amplitude, or in a coefficient that we call t. And t squared is certainly the probability, because it is the modulus of the wave function. If I take the modulus of this wave function, this disappears, right? Because the complex conjugate goes away, I get t squared. The same with 1 there, the same with the r. That's why I said The probability of reflection is r squared, and the probability of transmission is now t squared, because the oscillatory part goes away in calculating the modulus. That's why the coefficient is related to the probability of the particle being in that part of space. Okay, so we have two parts. We have in one situation, particles coming, incoming flux, will be interacting, and maybe part of it, or total, if r is equal to 1, everybody's going to go back. Now, there is a chance that the particle pass to this barrier, because there is a solution on the forbidden region, classically forbidden region, as we're going to show now. So, must survive to the other side. The wave function must survive to the other side in some conditions. And if it did happen, a particle really passed through the barrier without having energy for that. That's unique in quantum mechanics, right? Okay, so we go to region 2. Remember, we have the energy less than the top of the barrier. This is a classical forbidding region. We can't go through if we consider the classical concepts. But now we have the power wave function for this region, and let's see what's happened. Well, okay, we're going to write the equation as always, because the equation now must give us the solution for this physical situation. And this is the equation. The equation is minus h bar squared divided by 2m times the second derivative of the wave function in the second region, plus the potential times the wave function equal to the energy. Remember, we are here now, in this region. The energy is less than the V0, right? So I'm going to pass E to that side. So that's the equation. We know that this part is negative, and we're going to call this minus Q squared. Calling this minus Q squared, of course, we know that the E minus V0 is negative, but since we call minus, it means that the whole thing is positive. So Q squared is actually V0 minus E times 2m divided by h bar squared. Right? This is the real value of Q, and it's positive. You know, that's a nice way to expressing things. So what we have is an equation now that has the second derivative of psi in this region minus Q squared times the function, the psi in that region, equal to 0. So if it was a plus here, we know that that's oscillatory behavior. But when it's negative, we know it's exponential behavior. Therefore, the solution for this equation is actually a composition, but you know, it can be a positive exponential or a negative exponential. But since this is valid only for x between a and minus a, we cannot say that there is divergence or anything, so we cannot throw away any of those coefficients a and b. I call a and b again, I like a and b, right? So, but we know that on the Q, there is the V0, the barrier, and the energy. This is the difference, right, between the two, which will be an important relation, an important quantity. And the wave function is actually a sum of positive exponential and negative exponential. So we have the solution for this intermediate. This is a solution. So the wave function exists. The wave function square exists. There is a probability for the particle to be there. Something else does exist, which will be the flux of probability, as we're going to show later. But the wave function exists, has values. Therefore, the particles are now penetrating in the classical forbidding region. And what are the consequences of this? Well, the consequences of this is we're going to apply now the continuity of the wave function and of its derivative, because there is no reason for the momentum to be discontinuous in this system. So in x equal to minus a, the solution of the region 1 must match the solution of region 2. And the derivative, which here I represent by this prime, must be equal as well in that region. The same for x equal to a. On x equal to a, the solution of the second region must match the solution of the third region. And the derivative of the solution of the second region must match the derivative of the solution of the third region. So we actually made the wave function and the derivatives to be continuous. So this must be continuous, and the derivative must be continuous in everywhere in space, especially on the boundaries that determine the barrier. We have 1, 2, 3, 4 equations to deal with. And we have A, B, R, and T to determine 4 variables. So we have 4 variables that we don't know and 4 equations. So we have 4 variables which are A, B, R, and T to determine, because K and Q supposedly to be well known. The size of the barrier and the energy of the particle are giving numbers. You know, whoever prepared the system put the energy in the particles, and whatever is the physical situation that originates this barrier is there. We did not, those are known parts of the problem. It's very interesting because when we solve the set of equations, which I'm not going to do here by lack of time, but it's simple. You know, I mean, this is make it equal exponential, make it equal derivatives. It's very simple. And what we get at the end of the day when we do all the calculation, we get an expression for the coefficient of transmission square, or the t square, which is the transmission coefficient. And just for completeness, I'm going to just call these modulus to keep the same language that I was doing before. So there is a probability finite, because the k is not 0, q is not 0, right? Either k and q, they are not 0, and they must compose this transmission coefficient. So there is a real probability for the particle to pass through. So again, we made a barrier, we send a flux of particles, and these particles can pass through. And this transmission is real. It happens. And this probability of transmission is called tunneling. And tunneling is a very important phenomenon in quantum effects. Maybe it's one of the most important quantum effects in bio, because we have so many situations that particles should not be transported from one side to the other because of natural barriers. But they do. Or even in chemical reactions, there is no energy enough for a molecule to become something else, because it must transfer electrons to change the configuration. So there is a barrier there, but it does. It goes through. And that's tunneling. And the tunneling is a very important phenomenon, right? Maybe it will be one of the first applications that we are giving you related to the quantum effects. Now, we can show, once we have T, we have A, we have B, we can show that actually what's important here is the relation between what is reflected and what is transmitted. And by conservation of probability, of course, r squared plus t squared equal to 1. So once you know that you have an incidence on the barrier, either it reflects or transmitted in terms of probability. So we have the incident flux that comes, which is represented by that wave of amplitude 1. We have a reflected part, which is represented by that wave function with amplitude r, and we have the transmitted part to the barrier. That is the tunneled part of this. So we have this barrier now, which represent, a part of space where particle cannot exist, but it does quantically. And the reason that does quantically is because the phenomenon of tunneling is present. So tunneling is a name that we cannot forget now. And what is the tunneling? The tunneling is this penetration or the passing through a physical barrier of quantum particles, right? And that's a quantum transport, because electrons could be electrons that has to penetrate in some part of a natural barrier that it is in the biological system and everything, and we go through. Or even transmission of electron in the connection of neurons and things like this. It may well be the quantum is there all the time by this tunneling phenomenon. Tunneling is very important. We made a barrier, square barrier, but actually you can have any barrier you want, as I'm going to show to you. And that's the coefficient that we're going to work with. And of course, we can make approximation. We can say, well, Q is not as big, K is not as big, and we can make approximations of this and come up with expressions, right? As we're going to do next. But the tunneling, the concept of tunneling, is one of the key points of this quantum phenomena in biosystems, and that we have to deal with, and we have to learn well. And as you can see, it is fully predicted by the wave function. By solving the wave function, we are able to naturally get what is the probability, quantum probability of the system to overpass a physical barrier that is in front of it, without having energy for that. Because, if we had the energy enough, the particle just gonna pass through the barrier. That's easy. We will decrease a little bit the energy when pass, and then continues going. But it's not what's happening here. We did not have energy enough to bypass, or to not bypass, by overpass the barrier. But the quantum mechanics help us with that. Maybe because of the tunneling effect, is that many things happen in life, including mutations, including many other things that depends on system going from one situation to the other, where energetically speaking, we will not have energy enough to overcome everything that needs to get there. In terms of visualization, as I told you, it's always important to visualize what's happened. So in terms of wave function, we have here the composition of what's coming and what's returning. And then we find the barrier, and then here we have a real, I'm plotting the wave function square. So you can have a actually view of the probabilities density. So here you have this oscillatory density that basically is the particle spread in this space. But in the barrier, there is this exponential decay. The particle will decay from minus A to plus A until reach the other part, and then continues with a transmission. Of course, an amplitude is smaller than the incident, and the reflected is combined here with the incident, so we don't know exactly. If the barrier is very big, very wide, of course this will continue decay, so the amplitude of transmission, of tunneling, will be less. So this is the tunneling, right? Is this part that passes through the barrier. If the barrier is very high, also if it is very high, if you look to the exponent, if the barrier is very high, as you saw, the exponent, this term's k will be very big, and the negative part of it will kill the wave function a lot, right? So the transmission will go down because the sine square, this expression I did not explore, but is 2k q square on the numerator divided by k square, q square, everything square, sine hyperbolic square of 2qa plus 2qk square. This is the expression. But this term has the exponential at. As you know, the hyperbolic sign is a sum of e to the plus qa and plus e to the minus qa, right? That's going to appear here. And then it goes up, and then I may have this negative exponential really shooting down the wave function. And that's this exponential decay you observe. And then continues the oscillation, right? Now, one thing is very interesting here. If you look at the solutions we have, the momentum of the particle here was k, and here is k again. So there was no dissipation of energy. Now, why this amplitude is smaller? Because the probability is smaller. But once the particle passes, it has the same energy that before. It's not that this slowed down the particle. This did not slow down the particle, only reduce the probability of coming to the other side. This is very important. 2 notes. Okay? Very important. Now, if you have a high momentum, you know, which means large K, that's high momentum, we can go and do some approximations on the expression of t squared that I gave to you, and you end by having basically, and the dominant term of this hyperbolic sign is the one that's negative on the top, and you can show from that expression easily that by neglecting a few things, if k is too big, you may neglect the other terms compared to the exponential one, because the plus exponential in the numerator is bigger, so you neglect some terms, and you end by having a simple explanation like this. So actually, in this case, the tunneling probability, the surviving of particle in the other side, the surviving of the particle in the other side is given by exponential of minus 4 qa. And q, you remember, is the v0 minus e, the q square, right? Times 2m divided by h bar square to the half, because q square is this quantity, right? If you remember right, this is the q square. So, you see that q depends on the difference between the energy that comes and the barrier. If that's big, it means q very big, and therefore this will be killed. If you have a long barrier, a higher barrier, V0 is big, right? Because this comes with a negative, we kill a lot. So if I have a very large, maybe this is killing further here. In the same way, if I have a most wide barrier, This is also killed by this exponential. That's a way to tell you that the tunneling effect will be less if the barrier is higher and if the barrier is wide. And normally, the way you see here comes with the product of how large is the barrier and how wide it is. The product of how wide it is and how high it is what determines the probability of tunneling. Okay? Very good. Now, we learned what's tunneling, and you cannot forget in your life, because the tunneling is the quantum pass through of a flux of particles through a barrier. And that happens also in some optics, right? That we're not going to have time to see now, but it is total internal reflection, frustrate total internal reflection is something that's important for showing the tunneling of the photons. Always you penetrate in a forbidden barrier, and that's a wave nature. It's very interesting. And and that's important because we know that as we're going to see some applications, that's determining many things to happen. Things that could not happen classically will happen with the quantum effects. And that's the importance of it. Now, we saw a square barrier, but normally in the real world, we have very little square barriers. Normally, I already told you this, it's very sensitive to the width and the amplitude of the barrier, and you have to know that. Higher barrier, less probability of tunneling. Wide barrier, less probability of tunneling. And if you want to compare, normally it depends on the product of the width times the height. Okay, so as I told you, normally the barriers are not square. They have all kinds of shapes, as we're going to see a few examples. Not today, but in the next lecture. So if we can have any shape, I choose any shape here. And we have an incoming flux. We have a transmitted flux. And we have a reflected part. But we learned how to solve a problem of a square barrier, right? A rectangular type. How we deal with this problem here? It's easy. We learn in mathematics that anything can be like divided in tiny little rectangles. In tiny little things, I can make this potential by supposing I have tiny little rectangular barriers that makes it. Right, and so on. So we're going to build up those potentials by making it out of tiny little barriers. If you add up those barriers, we make the potential, general potential. We have the influx coming. It has a chance to pass the first, the second, the third. And we know something that I teach you there on the basis of probability, in that little block of revision on probability, is that when I have independent sequential probabilities, like throwing a dice, rolling a dice or something, we saw that they multiply each other to give the final probability. Like, rolling twice a dice and ask you the probability to get one, you have to multiply the two probabilities. So we know that the probability that the flux passes through one barrier, and then it is a fresh new to pass the second, a fresh new to pass the third, and so on. So we know that the overall probability is the product of the probabilities. So if we divide the potential in tiny little barriers, we have that the overall transmission probability is the product. Because of the probability, because of this flux, we call e to the ikx. This we call r times I to the minus ikx. And we call this t to the ikx. We did that. So this coefficient square automatically is giving probability. It's so normalized that the sum has to be 1 and everything. Good. So we then can write that the total probability of a flux tunnel to this barrier of any shape is the product of the tunneling of each individual of those square barriers that I build up. Right? It's the product over the whole barrier, over the whole potential. And therefore, if I know the individual one that I just calculated here, I can multiply. And this is what we're going to do. We're going to divide this potential in tiny little barriers like this. And then we send a particle with potential, with total energy E. It will be incoming, that is a part reflecting, and that is a part in the tunnel. And the probability is the product. But you also know that it's very nice to transform product in sum. We like to transform products in sum because sum is integration in mathematics. So I'm going to get that expression that says that the total probability of transmission in this barrier is the product of probability of tunneling in each barrier. And I am going to apply the logarithm. And the logarithm of this is the logarithm of the product. But the logarithm of the product is the sum of all the logarithm over all the barriers. And we learn that, in some expression before, I made an approximation. You can go back and look at the approximation, that actually the probability is given by minus 2q times 2a. I put 2a here because there I had an exponential. If you look in there, the ti squared is proportional to the exponential of minus 4ka. But the width of the barrier that I used, the square barrier, is 2a. So I just trying to show to you that's 2 times the q times the width of the barrier for each individual barrier. This. So I just wrote this as 2a and 2q, right? Therefore, this is the dominant term because the rest of it I give you 1. And this is an approximation too. And then, the logarithm of t squared is actually the sum of all the barriers that make, all the rectangular barriers that make my potential times a delta x. So the width of each of the individual barrier here, I'm going to say that has a width delta x. And delta x is the 2a. Right? This is delta x times minus 2 times the q of each barrier. And the q of each barrier, we already saw that's root square of 2m divided by h bar square v of x minus the energy. So the sum here, if I make delta x very small, that it goes to dx, the logarithm of the transmission is actually the sum. I'm going to transform this sum over all the barrier in an integral. Depends on the energy that comes, right? And the tunneling on this. So that will be the total tunneling of the barrier. That's depend on the energy and everything. And then when I put here the value of the Q, which is here, that's Q of X, because it's the value of this Q that I calculate for individual barrier. Individual rectangular barrier that makes the potential. So the logarithm of T squared, which is the total transmission coefficient, is actually given by the integral, which is the sum, but I transform in the integral because I made the barriers very tiny. I made the barrier with width that's basically dx, and I transform the sum in integral. Then I just invert the logarithm, and I get that the transmission is the exponential of this integral. The exponential of this integral is very important. And will be used as the probability of tunneling in any barrier. If I know the barrier that's given by this potential, I know the energy of the particles, I know the probability of tunneling. Of course, the potential must be bigger, otherwise I'm going to have a negative. So if you have the energy of the particle with some value here, like this here, I have to consider that part of the barrier as the tunneling part, right? Which is evident here, because those are the ones. So I know exactly from where to where by putting the energy equal to the potential at that point. That's trivial. And I have an expression for the tunneling of any barrier I want. Because in bio application, the barriers will be very different. Now we know what's the tunneling, quantum tunneling. We know how to deal with the quantum tunneling for any barrier, even though we make all the concepts for a rectangular barrier, but we made any barrier as made of a rectangular barrier, and we got an expression. With that, we are ready to apply this in different applications, and that's what we're going to do in the next lecture. Bye-bye.